Hello everyone. In this video, I'm going to show you how to simulate the equations of motion for the 2 degree of freedom planar arm if we consider the viscous friction as well as the static coulombic friction and the dynamics of the brush DC motors. If you remember, in one of my previous videos, I have derived the equations of motion. An N-link manipulator in general, when we consider the friction and the dynamics of the DC motors, and these are those equations. And the video on my playlist robotics I can show you here. So this video here called Electromechanical Equations of Motion, this one has everything in it. Because in the previous video of that, I just explained the effect of friction and gearbox, specifically gearbox mostly, but here I also included the brush DC motor dynamics. So the end result of everything together is this guy. And we are going to apply this to the planar 2 degree of freedom manipulator, for which in one of my previous equations I have found for you the JVs and J omegas, the portions of the Jacobian for velocity, linear, and angular, the rotation matrices for each link, the inertia matrix for the links, and the gravity terms, the Coriolis and centripetal terms, right? I found all of those in one of my previous videos where I talked about equations of motion for an N-link robot using the Lagrangian method, if you remember, right? So I guess it was in this video here with these notes that I went over this example. And then I derived for you the JVs, the J omegas for this robot, the I matrix for each link, the rotation matrix for each link, and we calculated the D matrix. But then in this video, I explained that when you consider the effect of the gearbox, D becomes M, where M has some extra terms, and those extra terms show themselves in terms of the effects of the gearbox, because now, as you can see, the term that goes between J omega R and on transpose J omega is I total, and I total for link I is the I of link I plus the speed ratio or the gearbox ratio of gearbox I squared times the inertia of the motor at link I, right? So here the effect of the gearbox can really make this term, although this inertia of the motor is much smaller than inertia of the link, but when multiplied by a huge number R squared, the gearbox ratio squared, that term can actually be quite dominant. So if we do that, our D matrix becomes M matrix. We have not simulated that so far. We're going to do it today. The C of Q and Q dot is intact, is the same as that previous example where I calculated for you all of the Christoffel symbols, and then we calculated the matrix C of Q and Q dot as you can see here. So still the same thing. Your G of Q, the gravity terms are exactly again the same. So these are your G's, G1 and G2. So we are going to use them, both C and G. As I said, M we have to recalculate. We cannot directly use those D components that we had, right? We have to recalculate and call it M this time. And we have to calculate all of these other terms, the mu total, B total, and all of these other terms. And for them, I'm going to use these spec sheets of the DC motors that I showed you in one of the previous videos. We are going to extract each and every one of these parameters that we need from these spec sheets. So our simulation is realistic. So what do we do here? This is the utility function that I have, and this is the main script. Now in the main script, I have a lot of global parameters that the utility function needs. G of gravity, length of the two links, 20 centimeters, 12 centimeters, the mass of them 0.4 and 0.3 kilograms. These are the inertia matrices for links 1 and links 1 and 2, as you can see. I only have IY and IZZ, everything else is 0, and that I have explained in one of my previous videos. So you can see them basically here, right? This is your I number 1 and I number 2, very similar, except I'm using A2 and M2 instead of A1 and M1. Okay, so I still have the same thing. The rotation matrices are exactly going to be the same, no differences, as well as J omegas and JVs. They are the exact same thing that we found last time, right? And I explained them in my previous video. So these JVs and J omegas I am going to use in my code. Okay, so let's go ahead and see how I coded and how I use OD45 to solve. So these are the parameters for the robots, the geometry and masses of the robots. Then I go to the gearbox and to the DC motors, and here I choose both motors and both gearboxes to be the same for both of the joints. So which gearbox, which motor do I use? If we go back to here, for the gearbox, I choose this gearbox here, G51A, where the gearbox ratio is 19.7 to 1, right? So you can see that here. And then this guy has efficiency. One of the parameters that we need in our equations is eta, or efficiency, and that, as you can see, is 73%. So that's what I have here. What do I choose for my motors? For my motors, I need the viscous friction, I need the back EMF constant, I need the moments of inertia for the shafts of the rotors, I need the resistance, I need the torque constant, I need the basically Coulombic friction torque term or torque constant, I need the bearing viscous friction on the links and the Coulomb friction constants on the links. In this case, I neglect them. I assume that all the friction is only on the shaft of the motor and not separately on the link, so I just neglect them. You can, if you want, choose small numbers for them. I don't have exact data on it, so I just neglect it in this case. It's not gonna be a huge effect. And where do I get all of this? As I said, from the spec sheets of these DC motors. If we go up a little bit, you'll see that here I have the Coulomb friction torque. So this is your mu m that you have, and then viscous damping factor. This is your BM 1.1 e to the negative 5 and 0.0085. And these are these numbers that you see. This is the mu, and that 1.1 e to the negative 5 is what you can see here. Then going back here, I have a rotor inertia for each, which is 0.0016. So again, you can see that guy here, right? 0.0016. I know I have it somewhere. Bear up with me. Here, 0.0016, and that's only IZZ. I neglect all of the other moments of inertia of the motor shaft. And again, I assume the motors are the same. I have terminal resistance, torque constant, and back EMF constant. And here you can see them. This is 0.0263 torque constant, 0.0263, the same thing, Back EMF constant, terminal resistance is 0.72, which you can see here and here as well as here. So you see all of the data are coming from realistic DC motor and gearbox spec sheets. And now I have to calculate mu total, B total, and I total for each one of the joints. And we go by the definition that we had. If we take a look here, your mu total is mu of the link plus mu of the motor. Your B total, the viscous coefficient total, is B of the link plus the gearbox ratio times B of the motor. And these are what you can see here, right? These two. And finally, I for each joint is the I of the link plus the R of the gearbox squared times I of the motor. As you can see here, I total. And that I have implemented. Now I have this guy. And as I showed you, I have the rotation matrix for each link. I have JV and J omega for each link, and I have mass of each link. So now at this point, I should be able to calculate my mass matrix, and that's exactly what you see I do next in the utility function. So once I calculate all of these numbers, I declare them global variables, so the other code, my utility function, can have access to them without me recalculating everything inside the utility function. You see, I just call them global. So now when I form my rotation matrix for each link, and when I form my JVs and J omegas, all I need is to use that formula, correct? Sigma I goes from 1 to n. Here n is 2, so it's just going to be 1 and 2. M1 JV transpose JV plus J omega transpose R1 I total 1 R1 transpose J omega 1, an exact similar term, but instead of 1 you have all of them 2. Correct? So I exactly use this formula, this summation, and I calculated my coefficient of the acceleration terms M, the M matrix. As I said, C and G are directly coming from these previous calculations, so there is nothing really new about them, correct? This is your C, this is your G. The only thing is here I have C times Q dot. As you can see, the whole C is multiplied by Q dot. So I calculated this whole thing in one place and call it CQ dot in my code, as you can see. So this is the matrix C times Q dot. And if you multiply this C matrix that you see here by Q dot vector, which is basically Q1 dot and Q2 dot, what would you get? So if you do it with Q1 dot, this element is multiplied by Q1 dot, that element is multiplied by Q2 dot, and the same thing for row 2 happens. So let me write them down for you. Okay. Do one cleanup here. Write it nicely. So it is going to be negative M2 A1 A2 S2 Q1 dot Q2 dot, then minus M over 2 A1 A2 S2 Q2 dot squared. This is your first term, and the second term is only this guy times this. So this is going to be M2 A1 A2 S2 Q1 dot Q2 dot, the whole thing divided by 2. So here you can see that CQ dot here, this big vector. And then I have the G vector, which is exactly as I said, calculated for me. And that is this guy here, right? And that is what I have in the code. So this is this one, and then here, this one is the second element in it, which you can see. Okay, so I have those two taken care of, G, CQ dot, and M. All of those are taken care of. All I need to do is to get my friction terms with these diagonals and the forcing function on the right hand side. So the mu is very easy. You need just the mu total that you already calculated multiplied by sine of Qi dot. So it's going to be like sine of Q1 dot Q2 dot. And then each one of them is multiplied by mu total I. And then you need to make it a diagonal matrix, correct? So if it's like mu total 1 times sine of Q1 dot, mu total 2 times sine of Q2 dot, and just make that a diagonal matrix. So it is like this. Correct? That's what you need. And here, if you go and look at the code, I have mu total dot producted by Q dot vector in a sign, because my mu total is a vector. It has mu1 total and mu2 total in it. So I dot producted each element in it, or element-wise producted each element in it with sine of Q1 dot and Q2 dot, and then pass it to a diagonal matrix. So this is that first term. And then here, again, you see this is B total. B total, pay attention, that's a vector. It has both B total 1 and B total 2 in it. The same thing for Ka, Kb, eta, and R. And this capital R, which is the resistance. Each one of them is a vector. So that's why you see I did a dot product between them. So it's element-wise product. So the result of this whole thing is a vector. Added to this is a vector, and then you pass each one of the elements in that vector to be the diagonal element of a 2 by 2 matrix. So that's exactly what you see here. Ka, Kb, eta, R squared over R, right? Ka, Kb, eta, R squared over R, and then plus B total for each. And I took care of this diagonal. So now I have this matrix taken care of entirely, and this one, all I need is this guy here, and for that, again, I need to do product of R, eta, Ka, and R, and multiply by V. And again, you can see I have done that here. R, eta, Ka divided by R. This is that diagonal matrix multiplied by the vector of the two voltages. And then what I did, I took every one of these terms other than the MQ, every other term is gone to the left hand side, so that diagonal times V minus G minus the two friction terms minus the CQ Q dot, and then multiply by M inverse to give you Q double dot, and that's what I have done here. Now here I combined the Coulombic and viscous friction terms, all of them in a single variable called friction. So this is all of the friction terms, Coriolis and centripetal terms, gravity terms, minus the voltage terms or input terms, multiply by inverse, that's the Q1 double dot and Q2 double dot. And as you know, the command ODE45, which I have used here, can only solve first order ODEs. Both of these ODEs that I have here are second order ODEs. They have Q1 and Q2 double dots. So I have to convert them into two first orders each. So I need a total of 4 dummy variables. As you can see, the first dummy variable, I chose it as q1. Derivative of that is gonna be q2. Derivative of q, which is, and q2 here is really q1 dot. This capital Q is q1 dot. Then derivative of q1 dot is what? q1 double dot. Derivative of q2 is q2 dot, and derivative of what? q2 dot is q2 double dot, right? So this is a well-known method called the space method, or dummy variables, if you ever want to break your higher order ODEs into lower ones. But just in case you don't know it, let me emphasize that for you here. So in our case, as I said, I have two double dot terms. So the dummy variables that I will choose are like this cap Q. Number one is going to be Q1. Number two is going to be Q1 dot. Number three is going to be Q2. And number four is going to be Q2 dot. So these are my four dummy variables, or you might just call them anything else. You don't need to call them capital Q. You might call them capital Z or anything else. If I take a time derivative, now I have the time derivative of the first one, which is Q1 dot, and Q1 dot is Q2. The time derivative of the second one is Q2 double dot, and Q2 double dot is, based on our code, is the first element in that temp, because this temp is like both of your Q double dots in it. So the first element in it is basically what? Q2 double dot 1. If you don't like the word temp, I can change it to Q2 dot. It's not going to change anything, okay? It's just really a naming. The only thing that might be dangerous is you have to make it different from the actual Q2 dot. So I can call it Q2 double dot or DD dot. Okay, that makes it, or QDD dot, really. Q, not Q2. QDD dot or Q double dot. Again, let me do it like this. Okay, so I call it Q double dot, and so that's exactly what I have, right? This is going to be that Q double dot element number 1. Similarly, Q3 dot is going to be Q2 dot, which is going to be Q4, and Q4 dot, which is like Q2 double dot, is going to be that solution Q double dot that I found for you, element number 2. So these four things are exactly these last four equations that you will see. So I broke down my 2 second order ODs into 4 first orders. So now they are ready to be passed to OD for the 5 here. By the way, I'm solving my simulating the behavior for 2 seconds. I choose the initial angles to be like 10 degrees and 18 degrees for link 1 and link 2, starting from 0 velocities. And I use 12 volts and 8 volts for each one of the motors. And you might say, where do you get those numbers? I try to make them within or close to the rated voltage. If you see here, the rated voltage for these motors is 12 volts. They have 2 different rated voltages, 12 and a 15 too. In this case, I go with the smaller one. So you should be at 12 or close to 12, not really much above 12. In this case, I'm running the first one at the rated voltage, the second one a little bit below. In general, when you do it in a control algorithm, you have to keep changing V1 and V2 all the time. You're not going to use constant voltages. You're just trying to just go with a constant voltage, so the links will keep rotating in the same direction. but in general, these two voltages are your inputs that you have control on and you can change. So here, 12 and 8 volts, pass them to OD45, get the solution, and here I'm doing the plot of positions and velocities for you, and then I do an animation of the 2 degree of freedom planar arm with the voltages coming from here. So let's go ahead and do it. So this was the animation on the right for 2 seconds. These are the two angles. As you see, the angles keep increasing because the voltages are counterclockwise, so the angle should increase. And if you look at the velocities also, you see how they are changing. As you can see, although my torque is in one direction, but my accelerations are not really constant. And that is because of all the other terms that are affecting the motions here, including centripetal terms, Coriolis terms, friction terms, gravity terms, and so on and so forth. So accelerations by no means are constant. If you look at the slope of these lines, by no means are constant. And it's interesting, in the beginning, Q1 is a little bit bigger. I started it at 18 degrees and Q2 at 10 degrees, but you see Q2 very fast overtake Q1 until about 1.7 something seconds, and then Q1 catches with Q2 and then passes in terms of the angle. And if you want, I can simulate it one more time for maybe this time a little bit more timing, right? 10 seconds. And here show you that one as well. And the behavior of the dots is quite interesting, right? Maybe if I just remove the dash from their plots, they reveal a little bit better. Okay, maybe their plots look a little bit more interesting. Here we go. Okay, so you see, while each one is increasing constantly, but they are showing some oscillations too. And that is because now that the Q dots get bigger and bigger, now the Coriolis terms and the centripetal terms show their real effects. In the beginning, when it's small, those Q1 dot, Q2 dot terms, or Q1 dot square terms, the CQ dot is barely any noticeable. It's mostly gravity. Even the viscous friction is not like so big, because the viscous friction and the back EMF terms, if you look at them, they are all multiplied by Q dot here. Correct? So you see, they're all multiplied by Q dot. So when Q dot is small, literally some of the terms here in these equations are negligible. One of them is this, one of them is this. Okay, so you're really down to some very small Coulombic frictions and some gravity terms, other than the input voltages. But when Q dots get bigger, now these two terms show their effects and they cause all of those oscillations that you see in the motion. Okay, so hopefully this basic simulation was useful to you, and I will share both of these files, both the script, the main script, and the utility for you under the video description if you want to download and play with them and change anything and see the effects of any parameters. Feel free to do so, and I will see you in my next video. Thank you.